I'm going to talk to you today about asynchronous programming in C#5. Now, if you don't follow these things closely, C#5 is the next version of C#. Microsoft has said they're going to be releasing Windows 8 in the first week of August, and Visual Studio 2012 is kind of tied to that same release. So this is the next version of C#5 that's about to ship. And one of the biggest features, perhaps the most visible feature that's in the language for this, one of the biggest new features in C#5, perhaps the biggest one, is there is now language-level support for doing asynchronous programming. And there's a couple of reasons for this, one of which is that asynchronous APIs can make better use of the resources a machine has to offer. So if you're building server-side code and you're doing lots of I/O-intensive work, it's better to use asynchronous APIs because they tend to be a better match for how the underlying hardware and operating system work, and you can make better use of your server resources, get better throughput. But also, asynchronous programming is very useful on the client side. And with Windows 8 coming out, this is a particular concern for Microsoft. They want people to be able to write responsive applications, applications that don't bog down while they're waiting for things to happen. So for all those reasons, C#'s getting async programming support. So just to illustrate what I'm talking about, and I've just asked for the next slide, and I'm seeing nothing at my end. Oh, I've got the same slide a second time. That's good. Let's try again. This all went a lot faster yesterday when I was on a real internet connection. So just to illustrate what I'm talking about, classically, sort of with most operating system APIs, they tend to make you wait until they're done before they give you a result. So here we're looking at the classic web client API that's been part of .NET forever, and this is how you can download the content of a web page, and as you can see in this little code snippet, this goes on then to try and put that into some sort of text box on a user interface. And this is a really bad idea. This is not a good way to do this sort of programming. We're using a synchronous API, one which doesn't return until it's done. It will block the thread until it's finished the work that it's doing. Whereas an asynchronous API is a bit better. So the problem you tend to get with using synchronous APIs is you get this kind of gray screen of death. Your windows appear and then go not responding on you. Or on a server side, you might find you start to use a lot more threads than is productive. So basically, it's all bad news. So instead, you can do this sort of thing. And this is not new. This is not the new piece. This is something you've always been able to do. You can use one of the asynchronous versions of the API. Lots of bits of .NET support this. And this kicks off the work, but it actually returns more or less straight away. So under the covers, it will program the networking hardware to send the necessary networking requests. It will configure buffers to be able to receive the response. And it will basically just sit and wait for that to happen. It waits for the network card to do the transmit. It waits for the internet to respond. It's all very slow, and there's nothing much for the thread to do. It can just return back to you. Your application can carry on doing whatever it was doing, and then sometime later, you will be notified with some sort of callback. So this is asynchronous programming, and we've had lots of different ways of doing this in the history of .NET, but all of them have had their issues. So let's just quickly recap sort of how this stuff looks. Oh yes, I added a slide. So the key point I was making there is that asynchronous work does not necessarily have to involve a thread. The whole point of this is that we have things that take a while, are often I/O intensive, and will tend to just make you sit and wait, and we'll just block the thread doing nothing remotely useful. People often kind of have this misconception that to do useful work on a computer, you have to have a thread involved. But actually, when it comes to networking, that really isn't the case. I mean, my background was network device drivers, and I can tell you, most of the work of sending and receiving network data is done by the network hardware, and the CPU only gets involved at the very start and the very end of the process. Once the actual data has been received, then it can step in and start doing useful stuff. So you don't need a thread to be tied up, and so the asynchronous APIs simply make that explicit. Now, there's been several different ways that .NET has chosen to expose this idiom over its lifetime, several different asynchronous patterns that it has used from since version 1. The original one was called the APM, the Asynchronous Programming Model. That's been with us since .NET version 1.0. And it's the classic begin something, end something pair of methods. So that was very efficient. That was a very good model in terms of how it mapped onto the underlying operating system services. So the way that it presented things looked similar enough to how the kernel did things, but there wasn't a lot of inefficiency here. So you would call a begin method, that would kick off some work in the kernel, and then at some point later that would complete, and you could either get a callback when that happened, or you could provide some sort of waitable handle and it would signal it. This was very powerful, very flexible, very efficient, very scalable, but wasn't particularly straightforward to use, particularly in user interface code, because it would tend to call you back on some random thread from the thread pool, because who knows what the UI thread was doing at the point where the operation completes, so it just grabs a thread pool thread and uses that for you. So the version 2 of .NET introduced a different pattern called the event-based async pattern, the EAP. This did not supersede the asynchronous programming model. It was kind of complemented it. This provided a much more user interface friendly way of doing things. It was based around events, and it was aware of the threading issues that user interface code had to deal with. However, the problem with the event-based async pattern, well, it had a couple of problems. One is it didn't have a very good way of dealing with multiple concurrence requests. So if you had something where you might kick off more than one piece of work at a time, it couldn't cope with that. It didn't really have a good way of dealing with a particular piece of work in progress. The APM did, the Asynchronous Programming Model did have that, but it didn't make it particularly easy to use from UI code. And also, its abstraction for a piece of work in progress wasn't particularly good. We had this interface called iasync result, and there wasn't a whole lot you could do with it. So the TPL was introduced in .NET 4 to solve some of these problems and also to make it easier to combine work together. So one of the big problems with both the asynchronous programming model and the EAP was that if you wanted to do work that incorporated multiple things, it got really messy really quickly. So the TPL was designed to let you chain things together. So that's what was introduced in .NET 4. And now in .NET 4.5, there's yet another pattern, although this doesn't replace anything. This is kind of a layer on top of other stuff. There's a thing called the await pattern that C# supports. Visual Basic also supports it. It is a pattern that can be implemented on top of existing asynchronous services. And this pattern is what enables the language level support. Because Microsoft didn't want to bake too much dependency into C# on specific features of the framework class library. So they didn't want to make it an absolute requirement that you use the TPL if you're using this new asynchronous language support. For example, in Windows 8, if you're building a Metro-style application, so the new kind of touch-oriented tablet-based apps, and if you're using C#, well, the TPL is available, but none of the system APIs use it. Because the thing about Metro-style apps is that you don't have to use .NET to use them. You can write them in C++, you can write them in JavaScript, and so Microsoft didn't want to require the use of the .NET framework, and so they invented their own new asynchronous pattern specifically for the APIs presented to Windows runtime applications. And the C# team knew that they wanted their asynchronous support to work with that as well as working with the TPL. And so they introduced this extra layer, this await pattern, which I'll demo in a moment. And anything that supports the await pattern can use the new language features. So there is support on top of the TPL. .NET 4.5 adds support for the await pattern to the TPL, the task parallel library, so you can use tasks. It also provides support on top of the Windows runtime types, and if you've got your own asynchronous mechanisms, you're free to implement the await pattern on top of those as well. So it's probably time to take a look at some code. So let us see what happens when I try and screen share over this rather slow link. Let me just get that set up again properly. And less than encouragingly, it's not letting me click the button. Mind you, we had this issue yesterday, so I'll carry on talking for a minute because this thing sorted itself out when we did the dry run yesterday. So, the nature of the await pattern is designed to be efficient, to enable the C# compiler to use asynchronous APIs and to get a callback when they complete, to do continuation-based programming, but not to incur any overhead in the situations where the asynchronous operation actually completes quickly. So the idea is that we can use this stuff and know that when possible, it will run as efficiently as it possibly can. It won't kind of dump everything through the thread pool. It won't run everything through delegates if it doesn't have to. It won't allocate unnecessary resources. It only ends up doing the work involved in going asynchronous if it actually needs to. So where possible, it will actually run your code straight through. Because the way it presents the model to the developer is it looks like you're doing normal synchronous programming. As you're going to see when I show you an example of this, it looks almost indistinguishable from code that's just using ordinary synchronous APIs. Let's assume it ever lets me show you this. I have a green button. Right. Hopefully in a second or so you will now be able to see things. Or not. Well, I shall carry on talking a bit while this happens then, so you have something to listen to. So as I was saying, the idea behind the asynchronous language features in C# is that they shouldn't feel like async. And what I'm actually going to do when I finally get to do this demo is show you the kind of the transformation between the way you have to do things today and the way things end up looking with the asynchronous support. So I'm hoping that you can now see my Visual Studio. So I'm going to create a new project. I have to try and type this all one-handed as well because I don't have a headset for this phone. My headset only works over Skype, and we can't use that today, irritatingly. So let me create a simple... Actually, I'm going to make the WPF application because I want to show you the UI bits in action. You can use the async features in any of the .NET project types, as long as you've got .NET 4.5 or you're using .NET for Metro, it should all work. So what I am going to do here is very quickly add a button and a text box to my UI, so we've got something to look at. There's a button. And it's not letting me add an event handler. Let's go here. And I'm going to add a text box as well, just so we've got a thing to look at. And I'm going to retrieve some information over the internet and put it in the text box. And I'm going to do that initially the straightforward way, which is I'm going to create a web client. And I'll initially use the classic synchronous APIs, and you can see it blocking. So if I do text equals w.download string, and let's point this at my blog. That's not what it's called. It's called that. There we go. So this is going to do things the old-fashioned way, synchronously. It's not going to return till it's done, so this is going to block the UI. So I'm just going to give that text box in the user interface a name, so I can put something in it. And I'll fill out what comes back. So if I run this, one of the benefits of being on the flaky internet connection I'm on today, is that we should be able to see, if I click the button now and let go, I don't know if you can see that. Ooh. I've got the name of my blog wrong. Let me fix that and do it properly. EMG blog. Okay, so click the button. And it kind of stays stuck down for a couple of seconds. I don't know if you can see that because it's only staying stuck down because my network is slow, and that's the same network that you're watching that this webcast is being delivered over. So basically that's taking its time, and my application is completely unresponsive while that happens. I'm getting nothing back when I try and move the window around. So that's not a brilliant way of doing things. It will eventually come back, I hope, but that's obviously not going to be the way forward. So let's kill that. So what we would do before C#5 is we just use one of the asynchronous APIs. So there's a method called download string task async. It does the same job, but rather than returning a string, it returns a task of string. So this is using the task parallel library, the TPL. And, well, I can't now assign that directly into the text. What I need to do is make sure that once that task completes, and really that's going to be called text task, I'll say once that task completes, I want to run some more work. So I've kicked off some asynchronous work, and now I'm going to say, well, once that completes, please run the following code. So I'll wrap it in a lambda. And I've got to tell it that I want this scheduled on the user interface thread, not the default thread pool scheduler that it will use. So I have to pass a task scheduler. This is all stuff you do normally in .NET 4.0. So this says, please make sure that when you do run this continuation, you do so on the user interface thread. So again, if there's been a delay there, I've just called task scheduler.from current synchronization context. And now it should be safe to set the UI with some content because I'm on the right thread. But I've got to retrieve that content first. It's going to look like this. I'm going to get hold of that text task's result property. This little method here only runs, this inner method only runs when the task completes. And so I know it's safe to fetch that result property from the task because that will definitely be available by now because otherwise it wouldn't have called me back. So I should find now, if I click button, that the application is responsive, it's able to move around, it hasn't actually finished doing the download yet. And then eventually it comes back and shows the content of that web page. So this works, but it starts to get a bit messy. And this gets a whole lot more horrible if you want to start doing more complicated things. If I wanted to, for example, get hold of the headers of the HTTP response, I'd have needed some rather messier, some more complicated code, because I couldn't use the web client. I'd have to use the HTTP web request, for example, and that does things in multiple phases. The initial sending of the request and the getting back of the headers is one part, that's one asynchronous operation, but then there's a second asynchronous stage where I want to get stuff out of the body of the response. Because when you use the HTTP web request, it'll give you back information as soon as it has it. So as soon as it gets the headers back from the web server, it'll make those available to you. But the body might not be there yet. You might be downloading 4 gigabytes of data. And so that may come later, and you may need to use the asynchronous APIs on top of the stream class to actually extract those from the response. And if you think, well, how am I going to start doing all this kind of continuation-based stuff, and there's multiple phases? What if I want to loop around and iterate over the content of a stream? Iterating when you might have to break out of the loop and return and be called back later when the work completes makes it really hard to write sane-looking loops. You end up having to tear them apart by hand, and it's all rather horrible. So that's not much fun. However, it's really relatively easy if we use the C# async features. So now let me show you those. So here's what I'm going to do. I'm going to use the HTTP web request class, And if you've used this, you'll be familiar with the fact that the API is all defined almost entirely in terms of a base class web request, and you end up having to kind of cast things back all over the place. You know, that should work. And let's pass in the same URL there. Again, I apologize for the speed of the typing, but I'm holding a phone in one hand, which was not the plan. So I'm going to call this and do www.getResponseAsync, and that also returns a task. But rather than doing the continuation, let's have a look. That's going to return me a web response. Here's what I'm going to do. I'm going to say var resp equals HTTP web response. And if I just try that, it's not going to work because it's going to say, well, you've got a task of web response and you can't do the cast there. But if I put the await keyword, and this is the new language feature, and this requires me to mark the whole method as async, so let me add the async keyword to the method as well, then it's happy. So this reads like it's going to just sit and wait for that to finish. That's not actually what it does, though. It does actually continue on, and it will return at that point. And now I can get hold of the headers. So let's just very quickly do this. I'm going to put in the text out. I'm going to list all the headers that are present separated by new lines. So we ask for the response, which we're doing asynchronously, but we're using the await keyword to get that, and then from the response, I extract all of the header keys and stick that in the UI. Just to run this, I click the button. The thing's still responsive. I don't know if you can see this. It is moving around. And then a few seconds later, I get all the results back. So it was asynchronous. It didn't stop. It didn't block. And just to prove what's going on here, I'm actually going to move things around a bit. I am going to extract this into a separate method called doAsync work. And rather than waiting for that and button click, I'm going to make my click handler back into a non-async method. The compiler will say, well, hang on, you're using an asynchronous method here. Are you aware of this? Don't you want to wait for that? And in this case, I'm doing a demo, so the answer is no. What I'm going to do is show you the flow of execution. I'm going to print out a debug statement. Saying before. And another one saying afterwards. And I'm going to stick a breakpoint on that and a breakpoint on that so we can watch these things in progress. Let me just hide those away so we've got a bit more space. So I'm going to run this. I'll click the button, and we're in the debugger. It's hit my breakpoint inside of this async method. I'm going to create the request. And now I'm about to execute the line that does the await. I'm not going to step over this because Visual Studio 2012 does lots of tricks when you single step through awaitable code to make it look like things have happened in a sort of sane way. It actually hides what's going on. So I'm going to breakpoint that. So I've breakpointed the very next line. And remember, I've also breakpointed in the function that's calling this, I breakpointed the line where this returns. So if this was normal execution, you'd expect that just to move straight on to the next line immediately. But if I hit F5 to let it continue, you can see it's actually returned. My doAsync work method has returned, and I meant to write that after there rather than before, but it doesn't matter. We can see it. We're in the debugger. So it's returned without having finished the method. Now if I hit F5, the application runs for a bit, and then half a second later, the work completes, Visual Studio breaks back in. Now I am back inside that method that we just saw already return. So this is what happens when you make your method async. It will trundle along as normal until it reaches an await statement. It does the operation, waits to see, has a look to see if that succeeded immediately, So did it complete immediately? If it did, it will carry on. But if it didn't complete immediately, it says, well, I'm an async method. I'm not supposed to sit and wait for things to happen. So I shall return having first set up a callback. So effectively, it's turned the rest of the method into a callback. And then eventually when the operation completes, it invokes that callback and the method continues. The thing that's clever about this, though, is it can do this for rather more complicated bits of code. So if I instead do this, if I say I would like to create myself a reader, so I can create a new stream reader, to read the text out of the response that came back. So I'm going to wrap this around the responses stream, and then do this while we're not at the end of the stream. I'm going to read from the stream a line of text. I'm going to do it asynchronously. So in .NET 4.5, Stream Reader has this read line async, which returns a task of string. So again, I'm going to use the wait keyword. If I can type today, and that should keep it happy. And now it's going to loop around here, and it doesn't really matter what I do with this. Debug, right line. I just send it to the debug output. So that's going to read the body of the response one line at a time. And of course, if it's a massive response, that could take a while. It's going to come in over the network. It's not all going to be there straight away. So sometimes this read line async will succeed immediately, because data comes in over the network in chunks. So chances are when we get the first line, we've probably also got the second, third, fourth, and fifth line. But eventually, we're going to read enough lines that we've read all the data that's come in, and we'll have to wait for the next chunk to come in. And at that point, this await is going to return from the method again. It's going to return control back up whence it came, and then arranges for the whole method to continue once that completes. But now we're in the middle of a loop. We've sort of returned out of the middle of a loop, and yet we can pick up from where we left off. Now, if you're familiar with the iterator support in C#, this will all seem quite familiar. Iterators let you do a very similar thing. You can use the yield return statement to return from the middle of a method in a way that you can carry on again later. So you haven't sort of returned for good. You've returned for a bit, and it's stored all the state necessary to pick up from where it left off. Under the covers, this is using something very similar to the iterator stuff. In fact, if I quickly show you, if I build this first, and then show you the code in ILDASM, this is the IL disassembler, which sadly forgets the font settings every single time you run it. So let me quickly make this readable. If I take a quick look at the do async work method, hopefully you can see some of that. Let me just fill up more of the space. So this, am I looking at the right piece of code? Yes, I am. This does not, look quite how I was expecting it to look, or indeed how it looked earlier today. Have I opened the wrong file here? Oh, sorry, yes. I'm looking at the wrong class. So what this does is actually create a little helper object of type do async work. That's a compiler-generated class, and that's where the real work happens. That's what I meant to show you. So that's actually this thing here. It has a method called moveNext, which again gives away the relationship between and the iterator support. And this is what I wanted to show you. So this is how the compiler compiles that method you were just looking at. Fairly simple method, creates a web request, gets hold of the response, gets hold of the stream, and then iterates through the stream in a loop. Well, actually, the first thing it does is it gets hold of some state variable and uses that in a switch statement to kind of jump into various different bits of the code. So this is branching into different pieces of the method depending on what some state variable is set to. This is how it picks up from where it left off. Every time it returns, because it's blocked by some operation that hasn't finished yet, it updates a little integer variable, this state thing here, and then updates that to say where it had got to. So the next time it runs, it can jump straight back to where it was before. So if we look, I can find one of the things that does that. So yeah, you can see it's doing it here. So basically this is storing something in the local state. So basically it does that and then just returns back to the caller. So that is how it manages to do stuff under the covers. It's tearing the method apart and is turning it into a little sort of state machine on our behalf. One other thing to notice about all of this is I've not had to deal with any of the synchronization context or threading stuff. That has just worked. And that's because the async features are all designed to be aware of this. So I'm going to come back into the slides now for a bit. There's a bit more to talk about in those. Or at least I'm going to try to. Yep, there we are. So if I go back to the presenter view. So we have a question. Can you quickly explain the different threads, i.e. the UI thread and the code thread? Which one is the normally running thread? Is it the UI thread? And does asynchronous code run in a background or different thread? Yeah, that's a great question. So I was kind of talking a little bit about that, but let me just clarify. The C# language features for asynchronous coding detect when you're calling from a synchronization context. So when you're running from either a WPS user interface thread or an ASP.NET thread, anything that sets the synchronization context to be anything other than the default, it detects that and preserves that and ensures that when it picks up from where it left off, it actually runs using the synchronization context. So if you start some asynchronous work on a WPF user interface thread, it will continue to run on the same WPF user interface thread for as long as your method continues to run, no matter how many times it has to be called back because of asynchronous operations that have stopped. If you do it from ASP.NET, that has its own way of handling the synchronization context. It's not actually tied to a particular thread, but it will end up invoking you in a context where all of the HTTP pieces, like the request, the response, are available on your thread. It might be a different thread from the one that originally handled the request, but the context will be correctly set up. So it's using the synchronization context under the covers. And also, technically speaking, it's the CLI, it's the class library that does that for you. It's the class library that makes that work with its wrapper around the task class. That's where that all happens. In addition to that, the C# compiler also grabs the execution context, so things like security context will also be flowed, and any context local state. So basically, it does all the work for you to make sure that things run in the same context that they started running in, which is one of the things that makes this a lot less effort than the older patterns. It just does all that for you. So I am seeing nothing with the next slide. Oh, there we go. Okay, so this is just a recap. Basically, you call methods that return a task or anything else that supports the asynchronous pattern. It doesn't have to be a task. Task is one of the types that has built-in support for the async pattern. So, getting close to running out of time before moving on to Q&A. There's a couple more things I do want to talk about. Just quickly, I'm going to describe how this works under the covers. And rather than actually going through it on a slide, I'm going to go back to the code. So let me restart that session, which should be quicker this time. Yes, it is. Good. Right. So just to show you what it looks like by hand, I'm going to add a second button. So I've got a second method. And again, it's not letting me attach an end of the day for no good reason. Let's do it that way. Right. So if you wanted to see what it was doing by hand, let's do another web client. I'll make you watch me type in the URL now. This is all going to be just log virtual. So this is going to be the task that comes back representing the download of the string. And the first thing that the C# compiler does, if you're using the await keyword, is this. It says, I want an awaiter to represent the operation in progress. And this is why C# doesn't care what type you're using. It's why it works with the TPL and with Windows 8, Windows runtime stuff. Is this says, well, as long as there's a get awaiter method, I'm happy. And it will expect the object returned by getAwaiter to provide certain facilities. It doesn't care what the is as long as it offers, for example, an is completed property. And if it is completed, then it will just go ahead and do whatever work it was going to do. And it gets the result with another method, which it expects all these things to have. So one of the things that the awaiter pattern is required to provide is a getResult method that returns the result of the completed work. So this is what I meant earlier when I said if the asynchronous operation turns out not to run asynchronously, because sometimes they do complete immediately, it'll detect that and go, oh, well, fine, we'll just go ahead and do the work immediately. But oops, if not, then it has to basically arrange to do the same work on a callback. So one of the other things it's going to expect the awaiter to provide is this onCompleted method, and here we pass some sort of delegate. And actually this is going to do the same work as we did here. So what I'll do is I will factor that out into a method called complete. And I'll just call the same thing here. This is slightly less efficient than what the compiler does, because the compiler would actually put all this code in one big method with that sort of hairy state-driven switch statement to decide what to do next. So it just keeps calling the same method again and again. I've chosen to add a separate method. But the effect is much the same. Basically, if the work completed immediately, then we call that complete method and go ahead and do what we're going to do. If the work didn't complete immediately, we call the awaiter's onCompleted method, passing it a delegate that it will invoke once it's finished. And that delegate's going to be invoked back on the UI thread because the awaiter implementation that is returned from a task does all that for me. And then again, we'll just call the complete method. Incidentally, this example has revealed what type the TPL gives back when you wait for a task. We have a thing called task awaiter. That was generated for me when I did the refactoring. So that was what I wanted to show you. That's basically how the pattern works. So let's return to the slides. One more thing I should talk about, three more things I should talk about before I open to Q&A. One particularly important thing is exception handling. Exceptions that occur inside of asynchronous methods are handled correctly. So if something throws an exception and you've got a try-catch block, it just works. If you've got a using block, it just works. And if you've ever tried to write exception handling code or to try to use using blocks with the TPL doing things by hand, you will know what a big deal that is. Now, am I still connected? Because I'm not seeing any slides. Yasmina, are we still on?
We sure are. Are you not?
Okay, so it's just me. You can't see anything. That's fine. That's good. So yes, the TPL has an idiom for packaging up exceptions. So when a task fails, it keeps hold of that, and then when you go and look at the task completion status, that will be thrown back out at you. The awaiter wrapper we were just looking at that the C# compiler ends up using ends up having that exception thrown back out at you. Even if your method has had to return and the operation has failed off asynchronously at some point and has called you back to notify you of that, it all just works in exactly the same way as it would do with normal exception handling. Now, I've inadvertently skipped over a slide here. This other thing I wanted to talk about is implementing async methods. So this is the other thing that the C# compiler can do for you. If you want to return a task object, well, you can do that by hand. You can do it the same way you would do in .NET 4.0. You can create a task completion source and then set it to complete when you're done. But if you return either task or task of something, and you mark the method as async, the C# compiler will provide task for you. And you can just return the result you want to. If you look at the code on this slide, you'll notice the return type is task of string. But if you look down at the bottom, the return statement is returning results, and result is a variable of type string. Not task of string, just string. And the C# compiler will turn that into code that completes the task. It will also generate exception handling for you. So if you throw an exception, that will get caught and put into the task. So if somebody else is using your asynchronous API, it will report the exception in the usual way for asynchronous operations. And also, if you have any await expressions in the method, like this one does, then again, it all just works. This, when you hit that await and your method kind of returns back to the caller is going to receive a task object that is not yet in a completed state. And then when that await continues, your code will continue to run, and it will then set the task returned by the whole method into a completed state when you finally return a value. So you get to write, again, what looks like perfectly normal looking sequential code, synchronous code that does one thing after another. But if you look at how this has to be done, if you do it by hand, if you've ever written this sort of code for .NET 4.0, you'll realize it really isn't as straightforward as it looks. You have to kind of tear things apart. Writing loops is a pain because you can't use the normal loop constructs because they have to span multiple methods. But with the new language features, that all just works just like you would hope. So we've got another question down there that's been pushed to me. Oops. Hold on. I think it was, can we please summarize the syntax on async and await? So async always goes in the method declaration after the accessibility, before the return type. So that's the only place you can put async. Oh, except if you're doing anonymous methods. This is a thing we did later in the day. You can also put async in front of an inline method, whether it's a lambda or a delegate. So always before the method kind of declaration, or always in front of the method if it's an inline one. In either case, it's a thing you say about a method, and it basically tells the compiler that you want it to do this kind of different way of compiling methods, so it can run differently. And where does await go? Await can go in front of any expression, literally any expression, and it can appear in the middle of any expression, so it's an operator. It's an operator that takes a single argument that directly follows it. So you can use it anywhere, that you can use an expression. Its only requirement is that the expression you give it must be something on which you can invoke a getAwaiter method, and whatever that getAwaiter returns has to conform to the awaiter pattern. So it has to provide an isCompleted property. It has to provide an onCompleted method to set up a callback. It has to provide a getResult to retrieve the results. So those are the only constraints. So that was pretty much everything I wanted to show to you. So let's move on to the questions and answers. So from a performance standpoint, is the new async and await more efficient than manually setting up the task or thread, assuming the task or thread is set up optimally? It is typically better unless you do things the hard way. So the way most people tend to use TPL or to use the other asynchronous APIs, or indeed threading, is they tend to pass a callback always. So like with my code, I did that continue with. So when I wanted to do some asynchronous work and then update the user interface once it was complete, I called continue with on the task to say, please call this next thing when that other task is finished. That's inefficient if the task happens to complete immediately, because it means that I end up pushing work through the TPL and through the thread pool when I didn't have to, whereas the C# compiler avoids doing that with its isCompleted thing. Now, obviously, you could write that by hand in C#, but it really convolutes your code. It makes life a lot harder. It's just way easier not to do that in C#4, so people tend not to bother. If you do it absolutely optimally, then it's pretty much the same. But be aware that the C# team have gone to some lengths to make this as efficient as they can possibly make it. And if you want to write code that is equally efficient, you're going to be writing something that is really ugly, because they've done all sorts of tricks that it's okay for a compiler to do and generate a code that no one's ever going to read, that you wouldn't want to do in your actual source code. So I would say that it's certainly in terms of the amount of effort you put in, it's almost certainly going to work better, perform better than it would have done unless you really go to extremes, in which case it will perform as well. So there's no advantage to doing it by hand now. Next question. Are there any similar C# await constructs expected in F# in the future? Now, I'm not an F# expert, but I am told F# already has this, so they got there first. What I don't know is whether they support the awaiter pattern. So they already did this, but they did it before the awaiter pattern was invented. So I would assume that they're going to update it if they haven't already, but I don't actually know, I have to admit. So I'm just seeing 3 questions in my inbox, and I believe I've answered all of them now. Am I missing any, Yasmina?
You're not missing any. Oh, here comes a new one. All righty, and I'll just put that in there for you. And folks, we just want to let you know we are at the Q&A portion of the event. If you have questions for Ian, please open your group chat, type them, send them in so he can answer those while he's with us. Back to you, Ian.
Yes, thank you. Sorry, I should have said, but since they were coming in, I was assuming you'd all got the hang of it, but yes. There we go. Sorry, it was taking a while to appear in my inbox. I thought I'd lost it. So, other than event handlers, why would you decorate a method with the async keyword with a void return type? Isn't it just fire and forget? Okay, so void is supported as a return type for async against the C# team's better judgment. They would rather not have done it. So you don't really want to do that. The problem with a void return type on an async method, so this is the problem with it is that if something goes wrong, you lose the exception, or at least there isn't an easy way to catch the exception. And also it makes it impossible for someone to know when your method is finished. So you essentially presented an API that takes a while and doesn't tell anyone when they've finished. So in practice, most of the time that you use async, you should return either a task, if you've got no data to return, or a task of something when you have something to return. So the only reason they support void at all is so that methods that have to be void can still use this. And that mainly means event handlers. So to answer the question, basically you wouldn't. So the question was, why would you decorate a method other than an event handler with async if it has a void return type? And the answer is you shouldn't. You should avoid that in general. So again, my question queue is empty right now, but I seem to have a slight time lag. Hang on, there we go. Any caveats, exceptions, or differences when working with WinRT rather than .NET? So, yes, WinRT, or the Windows runtime, Microsoft very helpfully decided to call the ARM version of Windows RT as well, just to matters. So the Windows runtime, the API for Windows 8, there are differences. So it's not using the TPL when you consume an API. You still use the TPL if you write an asynchronous method and you return a task. So that doesn't change, because if you're writing in C#, then you've got the .NET framework, and so you can use the TPL. But on the consumption side, it's always the async pattern specific to Windows 8. Now, in previews, it didn't always seem to call you back on the right thread, but I believe that was a bug. So I think, in theory, it should all just work fine once they've, in the RTM version. I think they've fixed that, in fact, by the RC as well. Are there any other differences? So a thing to be aware of is that the Windows runtime also provides other patterns. They don't just have a task-like thing. They also have a task with progress. So you can still use this with that, but if you want to handle progress notifications, you might need to do a bit more work. You might decide you're not going to use the await keyword after all, because you want to respond both to the completion of an event and also to the updates as progress occur. Other than that, I can't think of any, I'm not aware of any other exceptions. But that's not to say there aren't any, it just means I don't know what they are. So my queue seems to be empty and the refresh button is no longer lit up. So have we got any more, Yasmina?
Yes, one more. Just came in. Here it comes. Back to you, Ian.
Thank you. Is there any new IDE functionality to support await, i.e. debugging / visualizers? Up to a point, yes. The main thing they have done is they have meddled with the way single stepping works. So if you write code that uses all of this and you step through it, it all just seems like it's working normally. It actually tries to hide the returns from you. So if you are at an await and you do a single step on that, and the further execution actually returns back out to the caller because you're awaiting a thing that hasn't finished yet, it hides that from you. It doesn't show that happening. It kind of moves on line. At least that was true last time I tried it. It's possible they've changed this in a very recent release, but that's certainly what they were doing. And the reason for that, the reason that they chose to do things that way, was to make the debugging single stepping follow the logical flow of execution rather than necessarily following what it was really doing. Because remember, it tears your method sort of into a weird shape. It kind of splits it up into lots of pieces and does this funny state machine thing. And it's not always helpful to have that in your debugging, particularly since in the source code it looks like it did when you wrote it. So having those strange things can be unhelpful. As far as the visualizers are concerned, I don't think there's anything new. They've modified the stack trace so that knows when it's looking at these sorts of things. So it will try and show you what's going on. But it doesn't always know how you got to where you are. It'll just tell you that you're at an async transition point, if I remember rightly. So the only visualizer I'm aware of for this sort of thing was already in Visual Studio 2010, and that's the visualization around the TPL. So there is some visualization for tasks in progress, although that mainly focuses on thread-based tasks, ones that run on the thread pool, and the kind of tasks you end up returning from asynchronous methods don't. They're not the kind that schedule up the work item on the thread pool that sits and calls a normal delegate. That's not how it works. So actually you probably won't see very much at all in that a lot of the time. So no, there's not a lot of visualization is the answer to that.
And Ian, I'm not seeing any additional questions coming in. Is there anything you'd like to leave the audience with as we wrap up?
Well, just in conclusion, the purpose of these language extensions is to make it feel really natural to write this sort of code. It's to try and take us from the point where async required you to tear great holes in the structure of your methods. The whole point of this is to bring it mainstream. It's to make it an easy thing to do. It's to mean that the sort of mere mortal programmers can tackle this stuff in a way where it used to be wildly bewildering. So that's a good thing and a bad thing. Possibly the scary thing is it means sort of programmers who couldn't hack doing async programming before are now going to be able to do it. That may be a scary world, although for those of us who are consultants, that might be quite a lucrative development. But it means for those of us who have been doing it the hard way for a long time, life's about to get a lot easier. I'm working on a project right now where we're doing a lot of async on inside of a web service. And knowing that this stuff is here in C# 5 and that I can't use it because we're having to target C# 4 in this particular project is really painful. I can't wait for this stuff to be easier. So that's all I've got to say. So thank you all for listening.